Hey everyone, and welcome. Today we are diving into a really powerful and actually pretty simple idea that's at the heart of how computers learn to see. It's called max pooling, and it's a crucial piece of the puzzle in what are called convolutional neural networks, or CNNs. By the time we're done, you'll know exactly what it does and why it's such a game changer. So picture this. A neural network has just scanned an image, looking for all the little things. Edges, corners, curves, you name it. Its brain is now flooded with these super detailed maps of every feature it found. It's just swimming in data. So the big question is, how does it cut through all that noise to see the bigger picture without getting lost in the details? And that's exactly where the need for downsizing comes in. You see those feature maps we just talked about? They can be enormous. They're packed with information, which is great, but also really computationally expensive. So we need a smart way to shrink these maps, to make them smaller and more manageable, but, and this is the key, without losing the most important stuff. And that smart way is max pooling. At its core, it's a downsampling operation. All that means is it's a technique for making things smaller. It works by looking at a small patch of pixels and summarizing that entire patch with just a single number, the biggest or maximum value. It's a simple idea, but it has a huge impact on our data.
Okay, theory's great, but let's actually see this thing in action. We're going to walk through the mechanics of how this works step by step with a really simple visual example so you can see exactly what's happening.
To make this work, we only really need two key ingredients. The first is a filter, which you can just think of as a small window. A 2x2 window is super common. The second is a stride, which just tells us how far to slide that window each time. For our example, we're going to use a stride of 2. All right, here's the process. First, we take our 2x2 filter and lay it over the first little pool of numbers in the top left corner. Next, we just look at those 4 numbers and find the biggest one. Then, we take that single max value and put it in our brand new, smaller output grid. After that, we just slide our filter over by our stride of 2. And then, we just repeat the whole thing. Find the max, write it down, and slide over until we've covered the entire input. Simple as that. And look at the result. This shows the transformation perfectly. On the left, we've got our original 4x4 grid, and after running our little max pulling operation over it, we're left with this tiny 2x2 grid on the right. We've taken 16 numbers and condensed them down to just 4. The impact here is just huge. By using that 2x2 filter with a stride of 2, we literally cut the height and the width of our feature map in half. That's a 50% reduction in each direction. But think about what that means for the total size. We've actually reduced the total number of values we have to deal with by 75%. That's massive. So, okay, we know how it works, but now let's get into the why. What's the logic here? Why is this simple trick of just keeping the biggest number so incredibly effective? I mean, it seems a little crazy, doesn't it? We're taking 3/4 of our data, looking at it, and then just tossing it out? What's the point of throwing away all that information? Well, it turns out this aggressive downsizing has some incredible benefits. First, it massively reduces the number of parameters the network needs to learn later on. Fewer parameters means less number crunching, which makes the whole model way faster. It also helps prevent something called overfitting, which is basically when the model just memorizes the training pictures instead of learning the actual patterns. And, most importantly, it does all of this while still holding on to the most important features. The intuition behind it is actually pretty cool. In one of these feature maps, a higher number means the network is more confident that it found a specific feature, like a sharp edge or a distinct curve. You can think of these as activated pixels. So by taking the maximum value from a region, we're essentially saying, let's just keep the strongest signal, the most confident detection of this feature, and move on. The source material for this explainer puts it perfectly, saying, and I quote, "We're able to pick out the most activated pixels and preserve these high values going forward while discarding the lower valued pixels. It's like we're only listening to the pixels that are shouting, the feature is right here, and ignoring the whispers." Now, just to be thorough, max pooling isn't the only way to do this. There's another method called average pooling, where you take the average of the pixels instead of the max. But honestly, in the real world, max pooling has proven to be much more effective for most jobs, so it's by far the most common one you'll see. All right, enough theory. Let's get practical and see how this actually gets built into a real model. It's really satisfying to see this whole concept boil down into just a single line of code. And here it is. If you're using a popular framework like Keras, this is literally all it takes. You just add a max pooling 2D layer. And look closely, you can see our two ingredients right there. Pool size, which is our 2x2 filter, and strides, which we set to 2. It's a perfect one-to-one translation of the idea we just walked through.
And here's the proof in action. Check out this sample model summary. Our input starts as 20 by 20. It goes through a convolutional layer and stays 20 by 20. But then, bam, look what happens right after our max pulling 2D layer. The dimensions are instantly sliced in half to 10 by 10. That's the downsizing effect we've been talking about, happening right there in the model's architecture. So, if you remember one thing from all this, let it be this. Max pooling is an incredibly powerful tool for making neural networks more efficient. It helps them focus only on the most significant, most important features, making them faster, less complex, and better at their job.
But that does leave us with one final interesting question to think about. This whole method is about a winner-take-all approach, keeping only the loudest signal in any given area. So what important, but maybe more subtle details, what quieter signals, might our network be tossing aside in the process? It's a fascinating trade-off, and it's right at the heart of how computers learn to understand our world.